So what I would like to do is continue talking about carbonates, or really adsorption processes. On Friday, I talked about adsorption processes, looking at a batch system and looking at CSTR systems, so completely mixed systems. We looked at powdered activated carbon for both batch treatment and a CSTR treatment. So now what I'd like to do is look at what we refer to as granular activated carbon. So here we're looking at some sort of a packed bed. Now this can be, as shown here, an engineered system. The same type of adsorption processes also occur in soils. We can look at a system, okay, where we have flow in and flow out. We measure the concentration entering and the concentration leaving. Now, I'm going to draw a system boundary around this column. And as usual, we've done before, we can write a mass balance where we talk about the change in mass with respect to time. This activated carbon column. Change in mass, if we're looking at the column itself, is the change in mass with respect to time 0. So if we're looking at removing a contaminant, doesn't matter what it is. Later on, we're going to look at total organic carbon. So we'll say this is the concentration in of total organic carbon. And we have the concentration out of total organic carbon. If we draw a system boundary around the column, is the change in mass with respect to time 0? The answer is no. And why is it no? Because what's happening over time is that more and more of that carbon is or more and more of that TOC is being adsorbed onto the column. So if we were to plot the volume treated versus the effluent concentration, what you would find is initially the effluent concentration, gotta love this pen, the effluent concentration would initially be 0, and then as the column becomes, or the capacity of the column becomes exhausted, so the carbon becomes filled up with the chemical that you're removing, in this case TOC, the concentration will start to increase, and eventually it will reach the initial concentration. So this will be C0. Okay, does that make sense? Because the whole premise of what we're doing right now is dependent on understanding that. Yes, no, at least one. No, couple of terms that we will need to use are empty bed contact time. Okay, that is the volume of the bed. That means the volume of the media divided by the flow rate. The other thing to remember is that the adsorptive capacity is finite. There's a fixed amount of adsorbent in the bed. And that's why when we plot the effluent concentration versus time, it initially will be very, very low, but will increase over time to reach C0. If you have any sort of filter, Brita type filter on your faucet, on a pitcher, same process occurs. That's why you have to change the filters on a regular basis, because the filter media, the adsorption media in that filter has a finite capacity. And if you don't replace it, eventually that media becomes exhausted. It can't take up any more contaminant, and it no longer becomes effective. Now, as I mentioned, the change in mass within our system boundary is not equal to 0. It's increasing as a function of time. So the process is operating at unsteady state. When we talked about the CSTR system on Friday, and I've posted that video, there we were looking at steady state. So we're looking at operating that system at steady state. This is not a steady state system. I just drew a typical breakthrough curve. This one is drawn here. Okay. Number of things to recognize. This area here shown, and I just highlighted it in yellow, is the adsorption zone. Okay. We can say that equilibrium, the way we model these systems, is that we assume equilibrium occurs in the adsorption zone. We have C naught here. As the chemical is being removed, or the flow moves down the column to this here is our adsorption zone, and denoted as Z sub S. Okay. The concentration, if I have a port here, the concentration at this point is Z0. That is at equilibrium. So it's equilibrium between the sorption, desorption of the chemical. Over time, that sorption zone moves down the column. So the height of the sorption zone doesn't change, but the sorption zone is moving down the column, eventually reaches the bottom of the column. And when it reaches the bottom of the column, we're at C naught. So we've exhausted all of the capacity of the media in the column. The time to breakthrough here is defined here, and it's defined based on process requirements. So, for instance, defined based on an MCL, maximum contaminant level. It could be defined based on the maximum contaminant level goal. It could be defined based on some other process requirement. Okay. So the concentration at breakthrough, or the volume of water treated to breakthrough, varies based on your process. We can also define a term V sub F, which is the velocity at which that adsorption zone is moving down the column. And as you can see here, the greater that velocity, the shorter the breakthrough time. Now, do we want a long breakthrough time or a short breakthrough time? Think about your faucet filter. Do you want a long breakthrough time or a short breakthrough time? Or a long? One long so that more is absorbed, and you don't want to be changing that filter, for instance, every day, every week, once a month. You want it to last a long time. So we actually want a small velocity so that we have a long breakthrough and time to breakthrough. This image is from the FE reference handbook. There they refer to the depth of the absorption zone. Often you'll see it referred to as the height. We also talk about terms the number of transfer units and the height of a transfer unit. The number of transfer units is equal to the overall change in the solute concentration divided by the average driving force. And that is equal to concentration from y1 to y2. So it's the integral from y1 to y2 dy of y minus y star, where y star is the equilibrium concentration. So it is a measure of the difficulty of the separation. 1 NTU, so a single transfer unit is equal to the change in composition. So with that change, dy, change in concentration, is equal to the driving force, or the force producing the change. The height of the transfer unit is a measure of separation efficiency. The smaller, this may seem counterintuitive, the smaller the height of the transfer unit, the more efficient. So think of it this way, okay? The smaller the height of the transfer unit, the less material sorbent you need to achieve a certain change in concentration. Therefore, it's more efficient. Okay. Also means the smaller the column that I need to achieve a certain level of removal. The terminology that we use, okay, is, as I mentioned, okay, we've got, let's just start here. We've got Z is the total carbon depth. Okay, this is total carbon depth. So it's the depth of our column. Z sub S is the depth or the height of the absorption zone. V sub T is the volume treated to total exhaustion, and we define total exhaustion as 95% of the initial concentration. V sub B is the total volume that we've treated at breakthrough, and often we will define that as 5% of the initial concentration, but know that that can vary depending on your process criteria. So, but for here, we'll use 5%. And then C naught is the initial concentration. And then VZ is the difference between the volume we can treat to breakthrough and the total volume we treat to exhaustion. Okay, so those are important. Now let's look at two different scenarios. Let's look at this. We'll refer to this as this first scenario, and we'll let VT equals 5,000 gallons. So we've treated 5,000 gallons of water to the point where we exhaust the carbon. VB is 3,000 gallons. So At breakthrough, we've treated 3,000 gallons. VZ is equal to 5,000 minus 3,000, or 2,000 gallons. Let's say the height of the column is 10 meters. So that's okay. So then the depth or the height of the adsorption zone using this equation here is equal to 10 times V sub Z is 2,000 divided by V sub T minus 0.5 times V sub Z, or 2,000. And that is equal to, put this in feet, 5 feet. Keep all US units there. Okay. So the height here of our adsorption zone is 5 feet. Now, let's look at a different carbon. And this carbon has what we would refer to as a sharp breakthrough. So this is the same, but what we see here is a very sharp breakthrough. Once we hit breakthrough, there isn't much volume treated before exhaustion. So with the dotted curve, V sub T now is 3,500 gallons. V sub B is still 3,000 gallons. V sub Z is now 3,500 minus 3,000, or 500 gallons. Z is the same, so Z is going to be 10 feet. And now Z sub S is equal to 1.5 feet. Which is the more efficient carbon? The one that is actually more efficient is the smaller height of the transfer unit. This is the height of the transfer unit. So it's smaller. We're using more of the carbon because typically what we will do is we will stop the treatment at breakthrough. So when we look at the difference in these two columns, okay, it's only this portion of the capacity that is wasted. On the other hand, with the first column, it's all this portion of the capacity that is wasted. So essentially, we can't use that capacity because we have to shut off the treatment at breakthrough. So for that reason, the dotted curve is actually more efficient. It's got a smaller height of the transfer unit, and we're using more. Okay. So the question is, presuming you can stop at breakthrough, a sharper curve is better. The answer is yes. And typically, you'll operate these to breakthrough. Okay. There are a few cases where you might operate it to complete exhaustion, but those are rare, and they typically involve what we refer to as a merry-go-round system. You want to use all of the capacity. So for instance, with radionuclides, you don't regenerate the column. You're capturing those radionuclides to stabilize and solidify them. So there you want to operate to exhaustion. Column 1 that you've just operated to exhaustion. Once it's at exhaustion, you're going to take it offline, but you've got a subsequent polishing column. That becomes 1, and then you move forward from there. Okay. So it's really only with that type of a merry-go-round system would you operate to exhaustion. So let's look at another example. And in this case, what we've done is we need to treat in this case, a phenolic wastewater. It has a total organic carbon of 200 milligrams per liter. We're going to treat that with what we refer to as fixed bed carbon, granular activated carbon system. We have a flow rate of 10,000 liters per day. The allowable effluent concentration is 10 milligrams per liter. Now, typically what is done is to run a pilot study. So start at bench or slightly greater than bench scale. And here we've run a breakthrough curve on a test column. And that test column contains 3 kilograms of carbon. The volume to breakthrough for the test column is 2,080 liters. The volume to exhaustion is 2,930 liters. A full-scale carbon adsorption column was designed to be 1.6 meters in diameter, 6.5 meters in height, and it contains 1,560 kilograms of carbon. What we will determine then is the height of the adsorption zone, Z sub S, or the depth of the adsorption zone. We use what was referred to as a scallop approach. We'll also determine the number of transfer units and the time to breakthrough. So C naught is equal to 200 milligrams per liter of TOC. C effluent is 10 milligrams per liter of TOC. And Q in is Q out, and that is 10,000 liters per day, or 10 meters cubed per day. So our test or pilot scale column contains 3 kilograms of carbon. So that's our GAC. The volume to breakthrough, we said, is 2,080 liters. Volume to exhaustion is 2,930 liters. What we will determine first is a specific volume to breakthrough, and that is equal to 2,080 liters divided by the mass of carbon. And that is, so 693 liters of water we can treat for every kilogram of carbon in the column. The specific volume throughput to exhaustion is 2,930 liters divided by 3.0 kilograms of GAC, and that is 977 liters per kilogram of carbon. So for our full scale column, we said was 1.6 meters in diameter, 6.5 meters in height, so that is Z, and contains 1,560 kilograms of GAC. Remember, V sub Z is equal to VT minus VB. So now we can calculate the volume to breakthrough in the full scale column. So that is equal to the specific volume to breakthrough times the mass of GAC, and that is equal to about 1,055,600 liters, or 1,056 cubic meters. The volume throughput is the 977 liters per kilogram. Remember, that's the GAC times the mass of carbon in the column, and that is equal to 1,523,600 liters, or 1,524 cubic meters. So the height, depth of a transfer zone, height of the transfer unit is equal to Z times VZ over VT minus 0.5 times VZ. And this is equal to 6.5 meters times 1524 minus 10256 divided by 1,524 minus 0.5 times this difference, and that is equal to 2.36 meters. So that's the height of the transfer zone, or the height of the transfer unit, same. The product of the height of the transfer unit and the number of transfer units is equal to the depth of the column. So the number of transfer units is equal to Z, which was the height, divided by the height of the transfer unit. So that is equal to 6.5 meters divided by 2.36, and that is equal to 2.76. So this column contains roughly 2.8 transfer units. And finally, the time to breakthrough is equal to the 1,056 cubic meters that we treat to breakthrough divided by the flow rate that was initially given, and that is equal to roughly 106 days. So just kind of reiterating a little bit, we don't have a lot of time. I think I'll just do the third problem on Wednesday. But just to reiterate, okay, we looked at a batch system, but we also looked on Friday at powdered activated carbon. So powdered activated carbon, it's kind of the consistency of powder that you would put on your body. Okay. There we added that typically to a rapid mix system. So we add GAC, we may add a coagulant, We go through flocculation, followed by sedimentation. And our sludge contains any precipitate. So for instance, if we added ferric chloride, this would contain ferric hydroxide. It would contain any suspended solids. And it would contain the powdered activated carbon laden with the chemicals that we were trying to remove. We can also use granular activated carbon. So in our treatment process, where are we likely to add that granular activated carbon? So this is a much coarser material. Where would we add? So kind of similar to medium sand, okay, in terms of size. Where would we add the GAC? Do we have some options? So think of a typical treatment plan. We have our rapid mix. So we're adding coagulant. We have our flocculation basin. We have sedimentation. What comes after sedimentation, typically? Exactly, filtration. And I added the screens before, so we have filtration. And then following filtration, we typically have disinfection. Where are we likely to add the granular activated carbon? There's two places. One is right here. So we can actually add carbon to the filters. The granular activated carbon is lighter than sand. It will tend to sit on the top. So when we fluidize that bed, and the particles settle, it will tend to be at the top. It tends to be larger in size than the sand. Tends to sit on the top. The other place is right here, and that's to add a column after filtration. Why there and not at the front of the plant? The reason is that we want to use the capacity of the column to remove the contaminants of interest. So for instance, if naturally occurring organic matter is of concern because of disinfection byproducts, what we're going to do is we're going to remove as much of that NOM as we can in the coagulation, sedimentation. And what we can't remove there, we'll remove with the granular activated carbon. Granular activated carbon is expensive, so we want to use it as efficiently as possible. Why do we not add powdered activated carbon to the filters? So why, perhaps we could inject powdered activated carbon just before filtration. Why do we not use powdered activated carbon, but we use granular activated carbon? What was the parameter that we used as a major design parameter in designing filters? And it controls the depth of the filter. Okay, we use turbidity in determining our backwashing, but what did we use what calculation did we do? We did spent a significant amount of time on it. So we use turbidity to control when we backwash. What's the other parameter we use to control backwashing? Exactly, head loss. Okay, head loss is a function of 1 over the diameter of our particles and 1 over the porosity to the 4th power. What happens if we use PAC versus GAC? How does that affect head loss? PAC is much finer. So if it's much finer, what does that mean in terms of the diameter of the particles of activated carbon? It's going to be smaller? Exactly. The porosity is going to decrease, so the head loss increases. So our head loss is too great. So for that reason, we use granular activated carbon. We will almost never use powdered activated carbon in a column because of the pressure losses. I can't think of a time when you would want to use it. And you will not add powdered activated carbon before the filters because if capturing that material is going to result in a very significant head loss. And you don't want powdered activated carbon in your effluent. So we use granular activated carbon.